We are starting back up with digital logic and digital design, and I'm going to cover a few topics today, and then at the end I'll have a review with whichever time we have left. I have a total of 65 minutes to go, so lots of opportunity. Whoa, look at this. There's other gates in addition to AND, OR, and NOT. In particular, an AND is a not AND. I kind of alluded to this before, haven't I? I kind of mentioned that, oh yeah, there is a not AND, which is basically a AND gate followed by a NOT gate. And it's actually cheaper to make a NAND gate than it is to make an AND gate. And it's much cheaper to make a NAND gate than it is to make an AND followed by a NOT. So in other words, a NAND and a NOR, actually using transistors, you can make very expensively. That's why NANDs and NORs are very popular, or historically had been popular for making circuits. So we'll look at some examples of that because they're relatively cheap. There's also something called an exclusive OR. And an exclusive OR is interesting. It's if one of the inputs is 1, then your output is 1. I should say if one and exactly one of your outputs or inputs is 1, then your output is 1. So for 0, 0, your output's 0, and for 1, 1, your output is 1. This actually is pretty useful later on when we start talking about adders. But just like there's an AND, NAND, OR, NOR, there is an exclusive NOR, which is a NOT of the OR. And, well, this is an example of what the transistors would look like. And, I'm sure I'm going to have people ask for the test. Do I have to know all this stuff right here? And the answer is, you have to understand it, but I'm not going to ask you to draw a gate using these transistors. That would just be nuts. And by the way, that's also another class. That's not digital logic. So let's take a look at our example. Remember that aircraft lavatory sign where we had we turned on this. We had an AND gate followed by a NOT, right? Well, look at that. There it is, just right there. By the way, do you remember there was a law? But what if you take this, De Morgan's law, and you want to convert it into ORs? Can you do that? So what was De Morgan's law? By the way, remember you have a one-page cheat sheet. What do you think would be good things to put on that cheat sheet? Everything on the what? Oh, everything on this PowerPoint. Yeah, probably. But remember De Morgan's law? I'm just going to go over so many of these so fast. Let's go back to De Morgan's law. If I missed it, there we go. That's not the definition of De Morgan's law, but there we go. Remember, if you have anything inside the parenthesis, which means it's an AND, right? And then you NOT it, that's the same as the opposite of, or I should say, A prime or B prime. And in the same way, if you have something inside, that's the same as A prime, B prime. Very good things to know. Man, you guys are going to get like hundreds on that exam, aren't you? Here's an example down here. Remember, I showed you earlier the NAND gate. Just by putting the little bubble on the front makes it a NAND gate, right? So because of De Morgan's law, Remember, you were doing the NOT gate and then you were ORing it all together. Well, that's just nothing more than a AND gate followed by a NOT gate, which is a NAND gate. So let's say you want to detect all zeros. So you can say, I want to detect a situation when all my inputs are 0. So in other words, f equals 1 when a prime or b, a prime and b prime and c prime, which means using De Morgan's law, you can convert that into a NOR gate. You could also do exclusive OR to find out if A is equal to B, A being a multiple bit number like A0. Okay, here, let's see, there's no on this. So we have A2, A1, A0, which represents a 3-bit number, right? And let's say this is 1, 1, 1, and then I have, of course, B2, B1, B0. This is an exclusive NOR, correct? So let's take this situation. When A0 is 1 and B0 is 1, the exclusive OR will give you a 0. An exclusive NOR will give you a 1. So that's a 1. And this is 1, this is 1, and this is 1. Well, these are all going to be the same, right? 1, 1, 1, 1. This will be a 1, this will be a 1. We're ANDing all 1s together. That's true. All right? So look at the example when that is 1, 0, 1, and this is 0, 0, 1. So what is our answer here? A1 is 1. I'm sorry. Let's start at A2 up at the top. A2 is 1. B2 is 0. What is the exclusive NOR of this? Exclusive NOR. 0. All right. A1 is 0. B1 is 0. The exclusive NOR of this, just remember up here, exclusive NOR, 0, 0, 1, right? And then this is 1, this is 1. From our table, this is going to be 1. 1 and 0 is 0. So obviously those two are not the same. Easy enough? Now, any Boolean function can be implemented using just NANDs. Wow, do you believe that? Well, if you want to represent a NOT gate, you have a one-input NAND or a two-input NAND tied together. So in this case, this is a NOT gate. Because if this is 1, right? 1 going into an AND gate will be a 0. It's knotted, it becomes a 0, right? This is a 0. It goes into the AND gate. 0 and 0 is 0. Through the knot, it becomes a 1. Pretty neat, huh? All right. AND gate. So a NAND is followed by a NOT, right? Or an AND gate here we go. If we have a NAND followed by another NAND, that's the NAND, or it's, yeah. So we have an AND gate, and then you take the negative, and we just showed up here what happens. It just becomes a NOT gate, right? Now, why in the heck would you want to do this? Instead of using a single AND gate, why would you do two NAND gates? So you're using the same part. In fact, you know, if we say we're going to use only NAND gates in the entire design, then you only need to buy a bunch of chips. You know that these used to come in little packages like this, right, with little legs? You familiar with that? Chips? Dip chips? Yes? I did it. I talked about it in Engineering 1202. Remember the pictures? Usually when you had a chip like this and you said on it it's going to be an AND gate, and it has a couple of connections through the pins to the outside world, you don't just have one in there, you have multiple ones in there. So you could still use one single chip to represent an AND, because here you've got, usually you have two of these NANDs in here.
Radio Shack actually still sells
You got to be kidding. That's why Radio Shack is going out of business. They carry stuff that people don't use anymore. It's interesting, you know, this is an example of programming in assembly language. You know, it's nice to know where we came from, but it's really not helpful to program in assembly language because it takes so much time to do so. So that's why we don't use chips anymore. That's why we use VHDL and FPGA boards. So an OR you could represent by a NAND preceded by NOTs. So here you go. So you have a single AND and, oh, preceded by NOTs. What does preceded by NOTs mean? So you're actually going to turn out with two NANDs followed by one final NAND that you're putting in. And you know, these are proved by De Morgan's law. You never know when something like this might be handy on a test. Hint, hint. Likewise for NOR. In fact, let's do this. Turn to your neighbor and create a NOT gate, an AND gate, and an OR gate using only NOR gates. We are back, and I asked you to say, okay, what about NORs, right? So, well, here's the first one I'll do for you. The completeness of NOR. There we go. So, if you want to make a NOT gate, well, it kind of works similar to a NAND gate, right? Because if you tie both of the inputs together, and here we go, A, B, a NOR will give you a 1. So in this case, since you have only one input, A, you're tying them together, so it'll kind of look like this line of the NOR gate. You'll end up with 1. And if A is 1, they're tied together, kind of looks like this line of the NOR gate, and so 1 will be 0. Easy enough, right? Yes? And so here we go. We had some suggestions by somebody here. Let's see if that's right. So it's a, oops, up here. So this is your, I guess we need to go through this and look to see what it is, right? So if we're looking for an AND, that's our objective, right? Let's say we do a NOR gate. That is just downright ugly. AB. Our objective is to get this to be 0, 0, 0, 1. So through the first AND gate, or through the first NOR gate, we get what value? We get 1, 0, 0, 0, right? You agree with that? And so, if we add a second NOR there, and you tie it together, then you actually get an inverse, 0, 1, 1, 1. Oh, that's not an AND gate. That's an OR gate. And so now we need to take a look at our last one. So now let's look at A, B, and so eventually, after the last NOR, we want to end up with 1, 0, 0, 0. So if we have A, you know, this is our goal. So if by chance we work with this and we run it through a 1, we take the inverse, we inverse that 1, 2, we get this one, we get this one, we get this, we get this, then we get this and this, all right? Well, let's look at this. We're doing a not or, right? So 1 or 1 is 1, but it's a NOR gate, so it becomes a 0. 1 or 0 is 1, a NOR would be 0. Well, that looks like it'll work out well. So what we now have is hey, that bottom one looks a lot better. So where's my guys I took this from? Trip to the prize closet. Have you been to the prize closet yet? You can go. And you know what? I think it's been picked over, so you can come to my office and see if there's anything good. It's not so much of a prize closet as it is a bag of stuff. So, on your cheat sheet, not only would I write stuff down like this, and like the NAND gate, but I recommend you understand it. All right? Yes, sir?
Okay, so for the first one that you did, you ended up making what?
I ended up making what?
An OR?
No, I made a NOR. Hold it, I made a NOT. Which one?
The one in the middle with like, you scribbled out something.
Oh, yeah, this is the OR gate. The whole thing is an OR gate. The whole thing is an AND gate. The whole thing is a NOT gate. And again, I'm going to scan these and put them online, so you'll see them anyhow. So lest you have to work really hard. But the important thing to do, even if you don't know how to derive it, at least understand if I say you do something using only AND gates, and I give you this, or I say only AND gates, I'm sorry, I give you a problem where you have to do an and you only get NOR gates, then you know what to pull up. Maybe I should give you a problem that you might, who knows, see on a test. You want to do that? So I give you this. By the way, I would most likely do something like this, or I may not. By the way, is that simplified? How do you know if it's simplified or not? Well, there's one way you could do it that's really easy. When A is 0 and B is 0, so A is 1 and B is 0. This is A1, B0 is right there. Okay? When A is 1 and C is 1, that's here, and oops, and here. And when B is 0 and C is 0, that's right there. So in the Carnot map, I could circle this, but that would just be extra. So this leaves me with B prime, C prime, and this looks like A, C prime. AC. Sorry. I did get that right, did I? Yeah, I got that right. Oh, did I? No, I got that right. Okay, so there we got that. And if I tell you, do this in NAND gates. Think you could do that? Well, let's do the full-blown thing, right? We have an AND here, correct? So we have an input of A and C, goes into a NAND, and it follows with another NAND. And how do we represent an OR gate? Oh, I wiped it out. Oh, you know what? In the notes, I didn't even put it in here. So an OR gate was a what? Wasn't it one of those? Followed by a NAND? Yes? Oh, hey, that would help. Was this the OR? Is that yes or no? Yes, all right. I notice a pattern here. Oh, that means I also need to have this over here. And oh, I'm going to have to There we go. Okay, you like that? Can you make this simpler? Does everybody see how I got to this step, right? Is that yes or no? All right, so one thing I should note, this is a not followed by a not. That's equivalent to a what? A wire, right? So two knots following each other is the same as one, right? Or it's just a wire. So you can actually get rid of these. So our concept will end up like this. Sorry. And again, these notes are going to be online. Yes, sir?
Why do those two things cancel again?
Ah. Well, would you agree that would you agree that?
Yes.
So let's look. When this is 0, this will be 1. When that's 1, this will be 0. When this is 1, this becomes 0. When this is 0, this becomes 1. Right? So and remember, I said that this is equal to that, correct? We showed that earlier. So it would lead you to believe that that followed by the same thing is equal to a single wire that you're connecting.
Okay.
So if you were to ask to do something like this, you had better make sure you minimize it as well. So that works out pretty well, doesn't it? Now, I wonder if there's a clever way of minimizing that to something else. I'll leave that for an exercise later, but we're not going to go over that. Alrighty, how are we doing for time? You got it? So the number of possible Boolean functions, if you think about everything that's going on When A is 0 and B is 1, you could work on it such that the output will always be 0 or the output will always be 1. Or the okay, let me go back and say this. There are 4 different combinations of this, and so, because there are 4 different combinations of this, each one of these has 4 different ways or possible functions from it. And so, if you look at across this way, if A is the input and B is the input and they're both 0, and you get out 1, and A is 0 and B is 1 and you still get out 1, and A is 1 and B is 0 and you still get out 1, and A is 1 and B is 1 and you still get out 1, that means that no matter what the inputs are, F is equal to 1, no matter what A and B are input. The obvious will be the AND gate right here is what we've seen before. The OR gate we've seen before. Now we've just covered the NOR gate. And don't forget, we also had the exclusive OR. So here's that gate. And we had the exclusive NOR. So there's that gate. And sometimes it really doesn't matter what B is. Sometimes your function will follow A no matter what. And so this is the situation for that, where it's A. This is where it's B. And likewise here, whatever B is, B prime will be the output no matter what A is. And in this case, A prime is 1, or will be the output no matter what B is. And then a couple of other of these, they're just they need more functions. All right, do I do this? I tell you, no, I like that. No. I think you're all freaked out about the exam, so why don't I just have a review for the exam? How about that? From that respect, the chapter summary says, what did we cover? Combinational circuits, switches, Boolean logic, Boolean algebra, representation of Boolean functions, combinational design processes, more gates. Since we didn't cover this yet, I can't put that on the exam. I was kind of hoping to cover that, but oh well. So, with that in mind, we will end this recording. Thank you very much.